Hello to you all, and welcome for joining me for a view on the future of AI. I will be sharing some of the work that IBM Research is working on. At IBM, we have around 3,000 researchers all over the world, and what they invent and build just blows my mind. So I'm really excited to share some of those projects with you today, specifically around the future of AI. Now in November I did a TEDx talk in Antwerp around AI and ethics. And in it I talked about where AI is fantastic today, where it's super useful, but I also touched upon some of the areas that have a reason for concern, where we should pay attention because sometimes people's lives can be impacted in a negative way by AI decisions. And I also touched upon some of the hype that is still going on, some of the fear sometimes has to do with press releases and what companies are saying. So today I want to take some time to talk to you about what IBM is doing to address some of the concerns that exist around AI. Let's start with this media quote about OpenAI. OpenAI built a text generator so good it is considered too dangerous to release. Now, what is that all about? That sounds like a bit of hype, right? And it also created some controversy in the scientific community, at least, because typically researchers share the work they are doing. That's how, we learn from each other in an open collaborative model. But in this case, OpenAI said, no, we will not release because it's dangerous. So what is this thing? It is called a transformer, a type of neural network architecture which is able to transform a text into another text. So you give it a begin text, say in English, and it can translate in this case into French. Now, why can this be dangerous? Well, it can also be used to generate text. So I can give it a begin text, some words to start, and then it can continue the sentence. To illustrate this, have a look at this sentence. It's a kind of children's riddle. There are 6 frogs on a log, 2 leave, 3 join. How many frogs are there left? Now, it's an easy riddle, yeah? You see that it is 7, of course, but our AI system says 17. So what is going on? It is continuing the sentence with this neural network, but it's clearly not understanding the sentence, okay? It has some inkling due to statistics that it has to be a number, but it doesn't understand what is going on. So that doesn't sound really dangerous to me, right? It's really making big mistakes. But let me give you another example. So here I chose the words Alan Turing was, and I asked the AI to continue writing. And here it's kind of writing the biography of Alan Turing. It has some facts in there, some knowledge, but let's see. Let's fact check this sentence. Let's look in detail. So he died on June 21st. That's not correct. It was 23rd. Okay, it's only 2 days mistake, small mistake. But he was actually 41, not 54. He died of cyanide poisoning. He did not get the highest civilian honor. He got the 2nd highest civilian honor, and on top he didn't get it for work on the nature of intelligence, but rather, of course, as we know, for his work in cracking the Enigma code, which was probably a decisive factor in winning World War II. So if we look more in detail, then this sentence that as a first glance it looks realistic, it looks well written, but if we look deeper, it's actually full of mistakes. And that's maybe what they are referring to in terms of dangerous, in the sense that if you don't know these facts, if you're not a scholar of Alan Turing, then you can be fooled. It can generate, reasonably looking, but still fake text. Now, our IBM researchers have created a system that can detect this. So what you see here in green are the words where our system, our AI system, has determined that these words are very likely to have been generated by another AI. So they are automatically generated. And if we look at the distribution, you see here clearly that most of the words in the sentence are green. So we have indeed detected that most of the sentence is artificially created by a machine, and we are also very confident. So this is good news, right? We can detect that it's fake, and we can also be very confident about this detection. So this is something we will need to, maybe put next to texts on the internet to help us determine if this is real or, auto-generated. But this exact same type of architecture is also useful in an unexpected kind of way. So I will take you back to your chemistry classes, where you have some molecules, reactants, which we combine with reagents and with conditions. So conditions can be temperature or pressure. You put it in the mixer, you stir, and then you get a product, the end result of the chemical reaction. Now, all of this we can represent with letters, which I'm doing right now. So I'm representing this reaction by letters, and now I can use it with the same text transforming algorithm I showed you before. And I can use it to determine or to predict the outcome of a chemical reaction without ever performing the reaction for real in a laboratory. So you immediately understand that this can significantly speed up the discovery that we can do. We can look for molecules without going to the lab, so we can actually be much faster about it. And what we also can do is go the reverse. So we can take it in the other direction, and we can start with a product, the end result that we want to achieve, and we can ask the AI how we can achieve it. So which are the reactants, the reagents, and the conditions that would be necessary to get this molecule as a result. And in times of COVID, we have combined this in a tool that is available free of charge to researchers, and that can be used to actually help find molecules that can be interesting in attacking the COVID virus. So this is an area I'm particularly proud of, where AI can be really used for good, for helping us, humanity, fight some of the big challenges. Now, there is a downside to this. These networks, they become larger and larger. The first network I showed you had 1.5 billion parameters. That's already a pretty big network, okay? This was February of last year. Then, almost end of last year, there was a new network created, Turing NG, which had 10 times the size, 17 billion parameters. And only, a week ago, there was a new network by OpenAI with, the mind-boggling number of 175 billion parameters. This network is huge. So in the space of little more than a year, we got a 100-fold increase in the size of the network. This is, I would say fantastic, but we also found that this network is not much better, or even not at all better, in the common sense problem that I showed you. So even this network, 100 times bigger, is not able to, complete the sentence about the riddle about the frogs. So we are making them bigger and bigger, and it turns out that bigger is not better, bigger is not smarter, it's actually not helping us very much. And the other downside, of course, is here an amazing, enormous energy consumption used for training such a network. So I heard one research team that to train one of these transformers, it took the pollution equivalent of 5 cars over their whole lifetime. So all the pollution by 5 cars over the whole lifetime of these cars, that same level of pollution was needed to train such a transformer network. The 175 billion example I gave you also cost $12 million to train. So, this is only for big research teams, for big corporations maybe, but again, not very useful. And again, in that case, only a 0.1% accuracy increase. So we're making them bigger, we're consuming more energy, more pollution, but it's not really helping us. So this is a problem, right? And I want to address with you, we saw some of the problems, right? The pollution problem, the energy consumption problem, the way that, the accuracy is not increasing. And I want to share with you some of the areas where IBM Research is working to address those problems. So the first area is hardware. How can we be more efficient to train networks. And we work on different levels. We work on the bits level, which is, classical computing, making those better. As you know, we built the 2 largest supercomputers in the world. We built at IBM. So we're working on that, making better processors with our power CPUs, having more cores in there, better caches, adapted for AI, mixed precision computing, all the good stuff. So that's one area. We still need classical computing. Other area where we're super proud and leading the pack is quantum computing. Fascinating, extremely promising. Will help us solve some of the great challenges in physics modeling. Not yet today, but it's accelerating quickly. Not talking about that today. I want to cover today the element of neurons. And what I mean by that is systems in hardware that are shaped like a neural network, basically. So we adapt the hardware to the software. And in this particular case, I want to show you this chip. It's a research chip. You cannot yet buy it, of course. And it is, are you ready? It is an analog chip. It's an analog chip. It's calculating with electricity, using the laws of electricity. So using Ohm's law and Kirchhoff's law to basically calculate with electricity the most common operations in training a neural network, which are multiply and add. And because we are doing that with electricity, we can be very fast. We believe more than 200 times the speed of current GPU approaches. And we can also be extremely energy efficient. It's not only because electricity, but also because we are avoiding the von Neumann bottleneck, which is, of course, the bandwidth between the processor and the memory. As you know, we need to copy, of course, always the data into the processor. This is taking a lot of time. There is a limited bandwidth. The speed at which we can do this is not high enough, and we're losing a lot of time. That's why, for example, we have things like NVLink to get a bigger bandwidth, but still it is a bottleneck. So what we're doing here with this chip is actually we are merging memory and compute. So the memory and the compute are the same. We call this phase change memory. And so because the compute is inside of the memory, we don't have to copy, and we're avoiding that bottleneck totally. So this is also one of the reasons why it's super energy efficient and super fast. So after the hardware, where I showed you how we're working with classical computing, the bits part, where we're working with quantum computing, as the way forward into the future, and also with these neuro-brain-inspired models that I showed you with the analog chip. Of course, we also need to work on the software, because clearly something is missing. Common sense is missing. There's no real understanding of the sentence, as I showed you. So what can we do about this problem? Well, to illustrate that, I will talk about neuro-symbolic AI, which is really the new approach that we believe in, that will take us to this future of general AI, where we have systems that can think like a human. It's kind of the holy grail. And we think we need a new approach, something else, something different. And to illustrate that, I want to go back to the past first, again to Alan Turing, of course, one of the fathers of computing as we know it. And he created, he had this in his mind, this idea of a manipulating symbols. So these symbols would be on a strip of tape, and they would be manipulated according to some rules. Symbols, that means we can calculate with things which are not numbers. We can do this, for example, we can work with chess pieces, which are symbols, right? Symbols representing, in this case, the chess pieces. And Alan Turing himself created a chess program. In 1948, he started with that. And in 1952, he tried to actually put it onto one of the first computers of the time. That didn't work out. So to prove his chess program, he played it on paper by calculating each move by hand. Took him half an hour per move, but he did it and demonstrated that it was possible. But I want to focus here on the symbols themselves, as I illustrated. So a chess program would have an inference engine, some kind of chess engine, and some knowledge base, some rules, some knowledge about how the pieces can move, and maybe some openings of grandmasters and things like that. Another example is here. If I take another type of symbols, on the left we would have Socrates, in the middle humanity, and on the right mortality, then we can imagine having rules like all humans are mortal, rule 1, and then rule 2, Socrates is a human, so our little inference engine here can infer that Socrates is mortal. So back in the day, even when I was studying 92, 93, there was this idea that we would build expert systems. We would by hand encode the knowledge of a certain domain in the computer, for example, medical knowledge, rule by rule by rule by rule. We would put thousands of rules into a system, and then out of that, with a rule engine, an inference engine, we would get a thinking system. That didn't work out for several reasons. One amongst that is that it's very hard to put all the rules into the system because there are so many of them. Secondly, they are changing all the time. Reality is not static. It changes, of course. And thirdly, sometimes the rules are contradictory. So the world is not black and white, so rules can be contradictory. So all of that made it very hard for these rule engines, these expert systems, to be useful. And then, of course, we got into the world of neural networks, which were very promising because we didn't have to code by hand the rules. No, the system would learn the rules directly from the data. So no human intervention required. We just point it to the data, it learns, and then it has all the information into its system. Now, as I showed, this is also not working out, right? Remember the little riddle? So we have a problem. The old approach didn't work for us. The new approach also has clearly limitations. There are fantastic books, by the way, on neural networks like this one, especially if you have children. It's very. This actually is a real book, by the way. It's like this 2 millimeter thick paper. There are better books if you really want to dive into that. The point I want to make is this one. We are now combining both approaches. So the old approach with symbolism and the new approach, or the more recent approach, with neural networks. We combine them into one new system, and we are using the strength of both, and we believe that this is our path towards general intelligence. So take, for example, a look at this puzzle here. It's again a children puzzle, and you have to move the little sliders to make the picture. And again, tada, we have Alan Turing. Okay. So this puzzle is very hard for a computer to solve if you don't give it any prior information. If you don't tell it which are the pieces, if you don't give it any of the moves that are allowed, if you just give it the end result, so you give it the begin situation of the puzzle and the end situation of the puzzle, you don't give it a simulator, so it cannot try 1,000,000 times, like, for example, they are doing with AlphaGo 0. So it only gets the begin image, the end image, and a number of example moves. That's it. That's all we give it. And still it is able to solve the puzzle by combining neural network technology with the symbolic solvers that exist for solving this kind of puzzle. I want to stress that it's much more than just doing image recognition on the puzzle pieces. It's really fusing the two approaches together. And the last example I want to give is this one. This is the project Debater. We are very proud of this one. It's a milestone in human-machine conversational systems. In this particular case, what it's doing is having a debate with a human about a difficult topic. And to do that, it has to understand what the human is saying. It also has to understand a large corpus of text. And with understanding, what I mean is that it can extract from the conversation or from the text argumentation and evidences. So claims and evidences which are in favor of, or against a certain topic. Topics which are difficult, right? Which are human dilemmas. For example, should cannabis be legalized? Or should gambling be banned? So we don't agree as a society on these topics. And here we want the computer to model them and to get into a conversation, a debate with the human. It can then form arguments and take the other side. So if the human is, for something, the computer can be against and can then write a speech. The significance of this is that now we can have a computer that can help us understand the other side. And I believe in terms of in times of polarization, when people are more thinking in black and white, I think it's good to have a voice or a help to understand what the other side is thinking and the arguments. So at least I'm not just in my own thinking, but I have an open mind. And I want to end with this quote by Pablo Picasso, which is supposed to have said around in the 60s, computers are useless, they can only give you answers. Now I want to use this picture because it makes me smile. I love the quote, even though I don't agree with it. I think this probably was true in the 60s, but we have come such a far way. We are now in a time where computers are showing us new directions, or helping us to be creative, finding new paths, accelerating discovery. And there are so many challenges in society, and we can use all the help we can get. We can use all the smart machines together with the smart humans, because these machines are not going to do anything by themselves, right? Smart machines plus smart humans can give us all the help we can get to solve some of society's largest challenges. Thank you.